Hello again, Year 7 mathematicians. I've seen a very nice video which Monica sent me actually as part of her project, and it's a very good video. It demonstrates some aspects of Pythagoras' theorem with 25 little squares, and I've made 25 little squares here. They all ought to be the same size. I'm sorry I did it in a bit of a hurry, but you get the idea. We've got 25 squares here, and we can easily separate them out into well, first of all, the 25 is 5 by 5, so it's 5 squared, and that equals 3 squared. There's the 3 squared. Plus, if I take these remaining squares and reorganize them a bit, I can do this sort of thing and show that the remaining squares are 4 squared. There we are. This is... Are they all still in the view? Yes, they're all still in the viewfinder. So we've got 3 squared plus 4 squared equals the 5 squared that we had to start with. But if we, whoops, sorry, kicked the camera about there. Camera's on a tripod, which is sort of awkward under my desk. So if we do that, that's fine, and it is true that 3 squared plus 4 squared is 5 squared. That's just a property of the numbers. But why does that apply to a right-angled triangle? Let's have a look at what we do if we take 5 of these squares and make that the length, the side length of a triangle. 3 of these squares, let's take 3 that are about the same, about the right size instead of the wrong ones. You could do this more carefully at home. I've done this in a bit of a hurry. 3 of those squares, how do we do that? Like that. And then 4 of those squares along here, like this. So now we've got a triangle, which is the gap in between all my squares. Can you see that that forms a triangle? The triangle is the piece of my desk in between all the bits of paper. Can we see that? Yes. The triangle is the bit of my desk in between all the bits of paper. Defined by a length of 3 on that side, 4 on that side, and 5 on this side. But is it really a right-angled triangle? I'm going to take the camera off the tripod and hold it as carefully as I can over the top of the triangle. Well, if Pythagoras' theory is correct, that should be the right angle. But it doesn't look much like a right angle to me, and I think the problem is that I haven't made my little squares accurately enough, and I haven't lined them up very well, have I? You can see that there's a bit of a gap there, and that's all wrong, and the lengths are all a little bit wrong. And the problem with the video, which contains that, and thank you very much, Monica, for the video, it's a very good video, is this might be a right angle, and it might not. It might be 89 degrees or 91 degrees or something like that. It looks pretty much like a right angle, and I know that if I made this thing very accurately and lined these things up properly and made this all nice and straight and used lots and lots of triangles that were exactly the right size, that we would get a right angle here. Yes, Pythagoras' theorem is true. But the little demonstration with the squares in the video doesn't prove that it's true, because it doesn't actually say anything about the triangle in between the squares. All we've got here is a gap that looks a bit like a right-angled triangle. Well, yes, it should be a right-angled triangle, but the video itself is not a proof of the theorem. And the video that I sent you earlier on, I believe, is a proof of the theorem. It's certainly accepted by other people. See if you can find other proofs. That's not the only one. But I like this demonstration, and you can do this for yourselves. You could cut out a lot of little squares, make them properly square, make them properly the right size. Mine are all higgledy-piggledy, all different sizes, because I did this in a bit of a hurry. But certainly worth exploring and worth having a look at. So thanks very much again, and I'll post this video now.